Okay, it's 9 o'clock in Japan. Good morning, good afternoon, good evening. Welcome to the morning session. We have 3 presentations and 1 invited talk. Before the presentation, here is the general instruction for a participant. Presentation is 18 minutes, and we have also 7 minutes for question and answer. Please keep the time yourself. English translation is available, and mute your microphone when not speaking. All presentation will be archived on your YouTube channel. If your camera on, your face may also be archived there. If you have questions, use Zoom's raise your hand button. You can also ask them at the design Slack channel. And we have post-session discussion about 20 minutes. You can enjoy informal personal discussion with presenters. And we organized with Zoom's breakout rooms. So let's move to the first presentation. The title of the presentation, please share first presenter, please share your slide. Okay, and the title of the first presentation is Predominant Instrument Recognition in Polyphonic Music using Convolutional Recurrent Neural Network. And the presenter is Lekshmi. Please start the presentation.
Okay, thank you, sir. Thank you for the introduction. So I am Lekshmi here. I'm a music signal researching professor doing research under Dr. Rajan, College of Engineering, Trivandrum, APJ Abdul Kalam Technological University, Kerala, India. My work focuses on predominant music instruments recognition in polyphonic music. So today in this presentation, I am going to present my work, predominant instruments recognition in polyphonic music using convolutional recurrent neural networks. This is a brief overview of my presentation. So the main aim of my presentation is to recognize predominant instruments in polyphonic environment using convolutional recurrent neural networks. Moving to the introduction. Music information retrieval is a very fast-growing field of research with lots of real-life applications. Among them, the predominant music instrument recognition is a highly challenging task. Predominant instrument recognition refers to the problem where the prominent instruments are identified from a mixture of instruments being played together. Before going to that, what do you mean by monophony and polyphony? Monophony means a single melody on an instrument, and polyphony means a number of instruments are being played together. Most of the research works involves the instrument recognition in the monophonic music, and my research differs from them by the instrument recognition in polyphonic music. This is because music in real life is mostly polyphonic, and the extraction of information from the polyphonic environment is a highly challenging task. The main motivation behind this is, first one is intelligent search of music. There is a huge demand of music because of the large number of music files available in the digital format. If an instrument information is included in tags, it will easily allow the people to search for a particular music they want. Next is audio enhancement. More instrument-specific audio equalization can be applied to the music. It also helps to enhance fundamental music information retrieval tasks such as source separation, and also helpful to identify the genre of the music. The main challenges are, first one is polyphonicity. In the case of a polyphonic music, the instruments are played various loudness and pitches, and also the interference of simultaneously occurring sounds make the instrument recognition harder. Next is data set. Getting a large data set would significantly improve the performance of the deep learning algorithms. So training data plays an important role in deep learning. Predominant instrument recognition till now. Bosch and Facherman introduced a comparison of sound segregation technique using an SVM classifier with a source separation technique in a pre-processing step. Han and Kim introduced a deep convolutional neural network for predominant instrument recognition in polyphonic music using MEL spectrogram inputs. Later, Kratimanos in 2021 used a set of augmentation methods for the instrument classification in the polyphonic music. Moving to the proposed method, it is conducted mainly in two phases, front-end feature extraction and back-end classification. For feature extraction, we considered both the magnitude and phase information. Mainly the researchers focus on the magnitude information and they just ignored the phase information. This is basically because of the difficulty in processing, difficulty in interpreting the phase information. Conventionally, the spectrum-related features used for instrument recognition considers the magnitude information alone. However, there may be additional information concealed in the phase which could be beneficial for recognition. So, in our method, we are introducing the phase-based mode GDgram along with the magnitude-based spectrogram and later followed by the fusion of spectrogram and mode GDgram. In addition to this, music texture features like spectral centroid, spectral roll-off, spectral bandwidth, chroma STFT, root mean square energy, and 13 MFCC coefficients are extracted and given to a deep neural network for training. And it is used as a performance comparison for the proposed task. And for the back-end classification, we used a set of networks like deep neural networks, convolutional neural networks, recurrent neural networks, convolutional recurrent neural networks, and we also used a generative adversarial network using waveGAN for the purpose of data augmentation. Next, moving to my data set. IRMA's data set is used in this work. Instrument recognition music audio signal data set is an annotated polyphonic data set with annotations of predominant musical instrument present. It has separate training and testing data with 11 classes. Training data consists of about 6,000 files of approximately 3 seconds long and is single labeled. On the other hand, the testing data consists of about 2,874 audio files, which is of variable length, that is from 5 seconds to 20 seconds, and it is multi-labeled, that is, it contains the presence of multiple predominant instruments. So we are training our network using the fixed length, single labeled or single predominant instruments, and we are trying to recognize the multiple predominant instruments from the variable length testing file. Next, moving to the mode GDgram generation steps. Mode GDgram, which is the phase-based information and is obtained by stacking modified group delay functions of consecutive frames successively. And group delay functions are defined as the negative derivative of unwrapped Fourier transform phase. It can be computed directly from the signal X(n) using the expression 2, the equation 2. The square term in the equation, denominator of the equation, makes the group delay function noisy. So, the modified group delay functions are obtained by replacing the term in the denominator by substantially smoothed version. Okay. The two parameters alpha and gamma are introduced to control the dynamic range of mode GD. In the proposed method, we choose alpha as 0.9 and gamma as 0.5. This is the MEL spectrogram mode GDgram of an audio file with acoustic guitar as the leading instrument. And we use the following specifications for plotting the MEL spectrogram and mode GDgram. Window size of 50 millisecond and hop size of 10 milliseconds, and MEL frequency bench as 128 for the proposed task. Next, adversarial audio synthesis, waveGAN. waveGAN B2 is used as the augmentation technique here. It is a flattened DC GAN architecture with same number of parameters and numerical operations as that of the DC GAN. It is trained using Bassettian GAN with gradient penalty. The output dimensionality of the waveGAN B2 is 65,530 samples corresponding to 4 seconds of audio at 16 kHz. A perception test is also conducted with 10 listeners to assess the quality of the generated files. Listeners are asked to grade the quality from poor to excellent, and a mean opinion score of 3.64 is obtained. This is for a qualitative analysis. The upper pane left and right represents the real and corresponding generated audio file with acoustic guitar as the leading instrument, and lower pane represents the mode GD grams of the corresponding audio file. And this is the block diagram of the proposed method of instrument recognition. So in the first phase, MEL spectrograms and mode GD grams are extracted and given to the classification network. And we used convolutional recurrent neural network for the network as the classifier. And during testing, the probability value at the output node of the trained model is considered as score in this experiment. Later, the values are fused to form the final prediction. And the fusion score is obtained by SF is equal to beta S spectro plus 1 minus beta into S mode GD, where S spectro is mode GD and beta are the MEL spectrogram score, mode GD gram score, and the weighing constant respectively. And figure represents the beta value for beta value versus test accuracy. Since beta is equal to 0.5 represents the maximum value, we choose that value for the fusion. And it is plotted for MEL spectrogram for the CNN, fusion CNN framework. And next way, convolutional recurrent neural networks. Because basically, convolutional neural networks are commonly used for the task of feature extraction. But it lacks the longer temporal information. RNN is suitable for handling time series as well as sequence of data and helps to summarize the temporal information very nicely. So we are using a convolutional recurrent neural network. In order to get the benefit from both the approaches, we are using a convolutional recurrent neural network in which convolutional neural networks are used for the task of feature extraction, and recurrent neural networks are added at the end of the convolutional layers to summarize the temporal information from the extracted features. And for RNN, we tried both the sophisticated recurring units like long short-term memory and gated recurring units with one input layer and 2 hidden layers, each of 32 nodes. And for CRN also, convolutional recurrent neural network also, we experimented with ZLSTM and ZGRU architectures. And this is the model architecture of CNN and CRN architectures. And for CNN architecture, we used a model exactly similar to that of the state-of-the-art hand model. And for CRN architecture, we used a model shown below. And batch normalization is used to increase the training speed. And 2 bidirectional LSTM units, each with 32 nodes, are used here. And bidirectional RNN are preferred compared to unidirectional RNN because it can consider the future timestamp representations also. All the networks are trained using Adam optimizer with a categorical cross entropy loss function, and softmax is used as the activation for the output layer. Next, moving to the performance comparison. The experiment is progressing thus in 3 phases. First, MEL spectrogram based, next mode GD gram based, then followed by the score level fusion based. And the performance of the proposed method is compared with that of the state-of-the-art HANS model and also an MTF, musical texture features DNN framework. And precision, recall, and F1 score is used as the metrics for comparison. Table below represents the comparison with the hand model. And in the feature extraction phase, we considered both the magnitude and phase information. And also we experimented with the ZNN, ZRNN, and RNN network architectures. In order to demonstrate the efficacy of our ZRN architecture, we experiment with the CNN alone, RNN alone, and later with CRNN. And next, softmax is used as the activation function for the output layer. And also we used a data augmentation using WaveGap. These are the experiment details. Experiment details and few audio files can be viewed from this site. So predominant, so in this task, predominant instruments are recognized from the polyphonic environment using MEL spectrograms as well as the mode GD grams. we introduced Morgedigram, which is the phase-based information, and sorry, 1 minute. Moving to the resultant analysis. This is the effort score for the experiments with data augmentation. Train D represents the training files available in the corpus, and train G represents the files generated by augmentation. And this is the table represents the results. And our fusion C-GRU architecture. Z-GRU architecture shows the best performance. And the micro F1 and macro F1 of fusion C-GRU are 7.81 and 9.09% higher than the hand model. This shows the importance of phase information in the proposed task. And this is the performance comparison on IRMA's dataset. And our proposed fusion techniques outperforms the existing algorithms on IRMA's dataset. And compared to LSTM, GRU performed better. And our fusion C-GRU architecture shows a micro and macro F1 of 6.15% and 7.4% higher than our fusion LSTM architecture. And it requires a well less trainable parameters compared to that of our LSTM and CNN architecture. And it reaches the convergence earlier, helps to train easily. And effect of data augmentation can also be observed from this table. Our micro F1 and macro F1 are 11.29% and 13.21% higher than our fusion C-GRU architecture without data augmentation. So moving to the conclusion. Predominant instruments recognition in polyphonic environment is addressed using Morgedigrams as well as MEL spectrogram. And we used convolutional recurrent neural networks for the task of the extracting the features with very less trainable parameters. And our fusion C-GRU architecture shows the best performance. And we also used a generative adversarial network using WaveGAN for the purpose of data augmentation. Experiment details and few audio files can be accessed from this site. And these are my references. Thank you.
Thank you very much for your very nice presentation. And we have 7 minutes for question and answer. Any question? Please. Okay, Professor Tetsuo Kitara.
Hi, thanks for your talk. Could you let me now listen to one of the audio samples you used?
Okay.
So I'm asking, okay. So I'm asking this question because it, for me, so it's not easy for, it's easy to imagine how difficult your task is, so it may depends on me what instruments are played at the same time as predominant instruments, and the balance, what's the balance of the volume between the dominant and predominant and non-predominant instrument and other factors. So, yeah.
How difficult, you asked me how difficult the task is because it consists of number of predominant instruments. Okay, that's all right. Asking.
Yeah. So I'm.
Okay. Thanks.
Yeah, I'm.
Okay, sir. Okay.
Yeah.
So it is a very challenging task because considering our data set, it is the training data consists of only 3 seconds single predominant instruments. So it has 11 classes. So first we train with cello, clarinet, flute, etc. It has only single predominant instrument. It's only single labeled, and it's only 3 seconds long. On the other hand, the testing data is a play. It is from 5 seconds to 20 seconds, and it contains multiple predominant instruments. So it is, even with a human beings, it is very difficult to understand what are the predominant instruments. Even a person with better musical knowledge can recognize some of the predominant instruments, but it's even a difficult task for human beings also. So it is a very difficult task for the convolutional neural networks or any neural networks for recognizing all the predominant instruments. And based upon the probability, it is recognizing the instruments. So the testing file has multiple predominant instruments and so variable length. And it has to recognize, we are training the network using the single predominant instruments, and the network has to recognize the multiple instruments from the variable length testing file. So it is a very challenging task compared to other monophonic, and even though we are training our networks, we are using the same training and testing data, but here the training data and testing data are entirely different.
Okay, thank you. So could you so if you post your URL of your audio samples on Slack, so I will check it later.
Okay, so sure, I will share the URL.
Yeah. On the Slack. Yeah.
Okay, sure,
Thanks so much.
Any question? So I have a question. You use the data augmentation technique. And did you hear the data after the data augmented?
Yes, sure, I heard it, but it is only 4 seconds long. So it is we are training, the training data is used for augmentation. So we are training using the 3 seconds audio, and the generated file is only 4 seconds long. We can't recognize, so since it's 4 seconds long, we can't recognize what the instrument is, but somehow it resembles the, if you are using piano, it resembles the sound of the piano. If you are using trumpet, it is producing trumpet. Okay, first I trained using 1000 epochs, the results are not, which is very much noisy, and later I trained using the GPU 2000 epochs, and I get some fair results. But the training for GAN also, the training data plays an important role, but here the training data is also very small, so the results are not that much excellent. I think so, because the number of training files available, maximum number of training files available for voice, it is only 778. So it is very low compared to that for training for GAN. By increasing the number of epochs and by adjusting some of the parameters and using a post generation filter, etc., I generated some of the files, which is good. Okay, it has some intelligibility of the sound. So only 4 seconds long, we can hear it, we can recognize it resembles the instrument sound.
Okay, thank you. Any question? So I have another question. How many numbers of the data set for running the network?
Means, how many numbers means? How many
yeah,
training data?
Data after the data augmentation.
Okay, after that, we use about 6,705 audio files are available in the corpus for training the waveGAN. And after data augmentation, after using waveGAN, we got about 6,585 files, and we compared using a similarity test. And after similarity test, and by hearing some of the files are most noisy, so I just removed it. And after all the corrections, I got about 6,585 files total.
So, yeah, if you use more data, the accuracy is
Yes,
yeah, maybe.
Sure, sir.
Yeah.
Because GAN requires requires a large number of data. Its accuracy actually or its perfection increases based upon the number of data. So here it has a limitation. But data augmentation results in an increased accuracy when we are training using a convolutional networks, etc. Because after training with WaveGAN or after data augmentation, my total number of files becomes 13,000, etc. So definitely my accuracy increases.
Okay. Any question? Okay, it's almost the time for next presenter. Thank you very much.
Thank you, sir. Thank you. Thank you, everyone.
Okay, please share your slide. Next presenter, please share your slide. The next presenter is Martin. Is not here. The title is a polytemporal model for musical scheduling. It's not here. So we have to skip the second presentation. The third presenter is Roberto. Are you ready? Okay, please. Okay, okay. Please share your slide.
Okay.
So
Hello.
the next presentation, the title of the next presentation is a framework for music similarity and cover song identification. So please start, Roberto.
Okay, thank you so much. Hi, everyone. My name is Roberto, and I'm here to present a framework for music similarity and cover song identification, which is co-authored by Emmanouil Benetos from Queen Mary University and Marcelo Queiroz, also from University of São Paulo. So a little bit of context. We have, with the emergence of huge datasets, the increasingly common approach to handle them with music information retrieval techniques, where we can handle the audio files directly. So analyzing the content of the audio instead of the metadata or some other extra information about the songs. And inside the music information retrieve world, there is a very important problem for us, which is the modeling of music similarity. And with music similarity, we are able to compute how similar are two songs from each other. And with this type of modeling, we can build a very strong base for navigation, organization, recommendation, and search inside a huge data set. So about the music similarity, there is no formalized concept of general music similarity. So we address individual types of similarity. So we have a modeling for melodic similarity and harmonic similarity and rhythmic similarity and timbre similarity, etc. And also a very important thing that the context usually is established by the dataset's annotation. So when we gather a dataset to work, usually the annotations is going to give us a hint about which type of similarity we are going to use. So if the annotations are instruments that are in the songs, we usually try some timbre similarity, for instance. Okay, so we built open source music similarity framework, which uses this pipeline here. So the first step of the framework is to extract audio features from all of the songs from the dataset. The second step, which is not mandatory, it's optional, is to aggregate local features, which are features computed for each frame of the songs, into a global feature, which is a global representation of the whole song. And the third step is to compute distance between every pair of song. And we formalized the concept of music similarity model as a triple, which is the extractor chosen for this pipeline, the aggregator chosen for this pipeline, and the distance chosen for this pipeline. And when we built all the models that we tested, we tried to gather as many possible options for each one of these three items of the triplet. So we have lots of extractors like tonal features and rhythmic features and timbre features, and we used a really large number. We also try to use a broad range of aggregators. So we use statistical summarization. So we compute for each dimension a single Gaussian, or if only one Gaussian is not enough, we can use Gaussian mixture models. We also use vector quantization and lots of other methods of aggregations. And the distance, we used spatial distance. So we have Euclidean distance, Chebyshev, and also we have Manhattan distance and others. And we also have distances between distributions. So for instance, if we want to compute the distance between two Gaussians, we can use Earth move distance, or we can use Monte Carlo distance, and lots of them. And also symbolic distance between symbolic sequence. One example is the Levenstein, which is the edit distance. It was going to say how many editions you have to do in the first symbolic sequence to get to the next one, to the second one. Okay, our framework has several outputs, and the first one is the music similarity matrix. So when you choose a data set and you choose a model, the framework's gonna, the first thing the framework is gonna output is a matrix that has this format. So this matrix is gonna save the similarities between all of the songs versus of the data set versus all of the songs. That's why the main column has the highest values, which represents the similarity of the songs with themselves. So in the position 0, 0, you have the first song, the similarity of the first song and each with itself. Sorry. And also we can see here that we have, for instance, in this cross-shaped area, we have in the middle a section that has high similarity values. That's why the color are stronger. And these songs versus the others, which are in the vertical and horizontal parts of this cross, you have like whiter and lighter, values, which means that these songs, they are less similar to songs outside this group here. So from this matrix, we can compute also numerical metrics that can give us how much, not how much, but how the model is differentiating songs from this data set. And the first metric that we use, it's called interclass similarity ratio, which gives us exactly what I tried to explain about this stronger colored area versus the lighter colored area. So this is just a ratio computing the similarity between songs inside this green area, which is a class defined by annotations. And so it's the ratio between the intra-similarity versus songs from this class and songs outside this class, which is represented here by this light red or pink color. So this ratio is gonna say how much the songs are similar to each other inside a class and with songs outside this class. And since this is a value computed for every single class, we computed a weighted mean for weighting by the number of songs inside each class for every single class in the dataset. So for this first experiment, we used 9 datasets to do a benchmark of the models. So we have more than 600 models using the combination of features, aggregators, and distances. And we used these datasets, which are very, they appear regularly in the literature. So we have basically 3 datasets that are annotated with musical genres. We have 3 datasets that has rhythms as the main information of the annotations. And also we have 3 datasets where the melody is the main information on the annotations. So we can try melodic similarity and rhythm similarity and other types. Okay, so the goal for this first experiment is to check from this huge number of similarity models, which one leads to the best results for the 9 similarity datasets that we gathered. So this is, so we have 690 times 9 values, but here where I only brought for you the best model for each one of the data sets. So these 3, the first 3 ones, we can see that, and I highlighted in green color here, we can see that they have the same feature. And this feature is melodic transcription of the song. And these 3 data sets are data sets that has annotations about the melody. So the classes are corresponding about a melody and people singing this melody or synthesized variations of these melodies. And it's very interesting to see that the feature for the best models are related to this information. And we can see also for the here for the MFCC, which is related usually with timbre, that the data sets that has genre, they are also correlated with timbre, which appears with this MFCC. And also I try to highlight it here, some of the aggregators that appears the most, such as vector quantization and some of the distance also. So this is a very nice summarization of the results. Okay, the second experiment that I'm going to talk today, it's about cover song identification. And we consider this problem as an application of music similarity because 2 songs, the original and the cover, or 2 versions of a third song, they have to share some music element between them. And we can grab this similarity using our models. And this is actually a little bit different problem. It's a retrieval problem. So you have a query track and you ask the system to give you n covers in a set of m tracks. It's a little bit different in the formalization, but we can use the models in the same way. So here the metrics, they change. The metrics that are commonly used in this problem, they change, and they are usually associated with the rank. So you can get 1 column of that similarity matrix, and you can order by the similarity of the original song and the other ones. And the rank here is actually the position of the first cover of the original. So you can have here some songs that this specific model thought it was more similar to the original one, but actually the first cover only appeared in the 5th position. And this is what we call the rank. So all the metrics are computed by these ranks. And the main one that we are going to use on the next table, 3 slides from now, uses the mean rank, which is only the mean of this rank of the first cover for all of the columns of the similarity matrix. So this is the main metric that we're going to discuss here. So we also gather 5 data sets that are available online, and they are all data sets, the annotation says, which is the original song, and the class is comprised of the original song and a lot of covers and or versions of this song. So the goal is pretty much the same. We want to see which music similarity models lead to the best results for every one of these specific data sets designed for the cover problem. And here we have the results. And it's very interesting to see also that the pitch contour segmentation appears again. And 4 of the data sets have this feature in the best possible model. And these models, they were ordered by the mean rank, which I said it was the main metric for us. And this is a very interesting finding for us, because the literature always report that the melodic aspects are the least variant between versions. So every time that we have a version or a cover song, lots of things can change. People change rhythm, people change the tempo, people change the harmonic, but usually the melody is the least variant musical aspect between versions. So this was explicitly emerged here for us with these models. And also, I want to do a shout out about the octave abstraction, which instead of comparing the songs by their actually MIDI number, we do like octave abstraction, which is just a modulo 12. So we compare like if it's a C or a D or a E instead of the C4 or C5. So this is what led to the best results. I also want to say that these 4 best results are almost the same. We also have here the which is the LCS, which is the longest common subsequence when we are comparing these melodic contour. And this is the only one from these 4 that didn't have the LCS. It has the Levenstein, which is a very similar technique to compare symbolic sequences. Okay, so here are the conclusions. As far as the authors are aware, this is the first benchmark of music similarity models made in the literature. A very important thing is that our models, they are fully explainable and human readable. This is a very important aspect of the models we choose. So I usually say that I can sit with a musician that never programmed in his life, and I can explain like a chromogram. I can say that the chromogram is showing the energy in the pitch classes, and I can say how this chromogram was summarized, like using, for instance, the mean of the energy for each pitch class, and I also can explain how to compare to global features with Euclidean distance. So every single step of the framework is explainable. We also have, I can't show today because we don't have time, but we also have a comparative discussion about similar models. So we have models that are very similar to each other with just a few tweaks, and we also do a comparative. So it it is good enough to sync the feature with the beats, or you don't have to do that to have better performance, etc. And the last conclusion, or sorry, contribution, is that we are publishing an open source music similarity framework. And here I have a very important external links. So the first one is for my thesis, from where this presentation came from. So this is the experiments number 1 and 2 from my thesis, and you can read everything in much further details over there. This is the link for my GitHub, where the source code for the music similarity framework is. Here is our auxiliary web page that does the bridge between the thesis and the code. So this is going to explain lots of things. So where to find things in the thesis in the code. This is a link that shows, and also shows all the results. Here I only showed the best ones, and in this link you can show every single result for the models and every model and every data set, sorry. And the last one is my email for contact. Okay, thank you so much. That's it.
Thank you for interesting talk. So let's move on, question and answer. Any question? Oh, Professor Tetro Kitahara.
Hi, here, can you hear me?
Yes.
Yes,
Okay.
yes.
So I'm interested in what happens if you have cover versions that is arranged into a completely different genres. Like I don't know if there are such a things, but jazz version of Queen tunes or something like that. You know, in such cases, melodies themselves may be modified in that case. So what do you think?
Yes. It is common not to change the melody, but it's not impossible. So the example you gave is perfect because every data set I used, we had like a jazz version or a orchestral version or instrumental version of a pop song or a rock song, and maybe this version doesn't even have a person singing. So these are the most difficult samples to compare. So I have I made a study on the outliers. So I made a study about which are the songs that has the worst mean rank, and some of this example you gave showed in these outliers, like a electronic instrumental version of a pop song that has someone singing. So it's a very hard problem to solve.
Okay, thank you.
You're welcome.
Any question? So I have a question. You made 690 models
Yes.
in the experiment. I think it's too many. All of 690 is important, or important model is not so many, and other is performance is bad. Yeah.
Okay. Now I understood the question. Right now, before the experiment, I can clearly see models that are very bad when you use them alone. So, for instance, I have a model that uses, let me think, RMS as its feature. So, okay, it was, we could have guessed before that RMS can't help us to identify similarity between songs, but we kept everything because in the thesis, the posterior experiments, we try to fuse the models. We try to use more than one model at once. So a bad model alone can help us in the future to give us a better result together with a strong model alone. So that's why we didn't discard anything. So we created the benchmark, and we started fusing things, and then we kept the 690. Also, as if you access that website that I said, we have the publication of the exactly how bad the models are. So that's also an important thing to show to everybody.
Thank you. And the next question, please, Professor Satoshi Tojo.
Okay. My question is exactly the same with Tetsuro Kitahara. He asked about the original song may belong to the different genre, but is sung by the popular singer, for example. And I'm interested in your notion of the interclass similarity.
Okay.
So if two pieces are classified into very different genres, then it may affect to the similarity. So how and who classifies such a class similarity or data set? My concern is that it depends on the classification.
Yes, it's something like this. Let's imagine a data set that has melodies. So you have one melody and 10 people singing this melody. And you have a second melody and 10 people singing this melody. This metric, which is called inter, is going to say if the similarity between this class, between the songs inside this class are higher or lower than comparing these songs with the similarities from songs from this class with the second one. So this is important to see if there is confusion, if the model is confused. So if the model thinks that people singing the melody one is more similar actually to the melody number two. So this is why we use this metric. It's going to say how much this class is well defined and separated from the other ones. Something like that.
Okay, thank you. Yes, yeah, I could understand.
Okay, thank you so much for your question.
Any question? And do you plan to develop this research furthermore in future?
Yes. Besides the expansion of the number of extractors, aggregators, and distances, I'm also planning to work with feature learning. So instead of computing the feature by hand, I can use feature learning. And also in the distance spectrum, we can use metric learning also. So instead of computing a fixed learning, we can try to learn a better metric that compare the songs. So we have plenty of things to do.
Okay, thank you.
Thank you.
Any question? Okay, thank you very much, Robert.
Thank you.
So we skip the second presentation. Second, Martin is there or not? No. So let's move on the post-session discussion. Okay. Post discussion is about 20 minutes, but we have more time so now preparing the breakout room. So, okay, thank you very much for preparing the breakout room. First, the presenter move to the breakout room of your presentation number. And after that, anyone go to the breakout room you want to talk. And you can enjoy informal personal discussion with presenters. So after close this session, please move to the breakout room. Thank you very much of all of you join the session. Thank you.
谷口先生。
あ、
Good
おは
morning.
ようございます。Good
お
morning.
はようございま
おはようござい
す。
ます。Good morning.
はい。じゃあ、よろしければ接続チェックを。
あ、はい、お願いします。
はい、お願いいたします。
と、よし。見えてますでしょうか ?Can you see my slide?
Yes, I can see.
So, let me restart the screen sharing. Maybe I have to check the audio as well.
Yeah, please you do.
I always forget to check the sharing the sound.
Sometimes me too.
あ Can you hear?
Yeah,
can you hear
I can.
me? Okay, okay, okay.
I can hear it.
Good, 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 good. So I think it's okay. Thanks.
Okay. Please hold on
Already?
until the start time.
Okay, thank you. Thanks.
これすいません。
はい、根本さん。
すみません。スライド見えてるんですけど、ノートも見えちゃってますけど。
そうですね。はい。
すみません。
谷口先生。
インシェアリングのあれを間違えましたね。
はい。
いいか。はい。
Please share the screen image. Okay. That's correct.
あ、また、また多分、音声のシェアを忘れた気がするので、
はい。
トライします。あ、なってますね。はい。
Okay, so please hold on this state until you will start the presentation.
Thanks.
Hello, everyone. This is a session of invited talk number 2 by Professor Tadahiro Taniguchi of Ritsumeikan University. We are very glad to welcome Professor Tadahiro Taniguchi as an invited talk number 2 today. I'm very excited to listening to his talk today. And first of all, I would like to briefly introduce him to you all, the audience. And he's an expert of artificial intelligence and robotics. And he has been very active and on the cutting edge of this field to open the horizon of the new area of AI and robotics. And he's very really active since he was a university student. And I have been also attracted by his symbol emergence framework, which is the topic of this session and his talk today. So I'm very excited, and I believe that his research and his research result must contribute to the autonomy and conscious, hopefully, for the future robotics and AI, and also contribute to the diverse of the music informatics. And also, I would like to put the another point. He is a very famous as the author of the AI textbook in Japanese. And really, actually, I'm using his textbook in my class in the university. And so they're very, very, very thin and very full of inspiration and full of exercises and very concise and elaborated. So I would like to appreciate his effort to write such a great famous AI textbook also. That's it. So I ready Professor Tadahiro Taniguchi. So that if you are okay with your preparation, then please start your talk.
Thank you very much, Ira-sensei. Thank you very much. So let me start this talk. So good morning. So thank you very much for inviting me as a keynote speaker. So I'm Tadahiro Taniguchi from Ritsumeikan University, Japan. So it's a great honor to be given this opportunity to present this talk at this conference, this symposium, great symposium. So I'll be talking about generative models for simple emergence based on real-world sensory motor information and communication. And actually, the PDF. This is a bit long talk, and maybe you want to go back and forth on your slide. So PDF has already been uploaded via Slack. So if you are interested, please have a look. Okay, so let's start the talk. This is a brief introduction of myself, and actually, this is textbook that Hirata-sensei kindly introduced. So, イラストで学ぶ人工知能概論 Introduction to the Artificial Intelligence based on with illustrations. So, anyway, my research topic, machine learning, cognitive and developmental robotics, and symbol emergence in robotics and language acquisition, and so on. So, basically, I'm not a researcher on computer music and music information processing, although I had a few works related to computer music with my students, ex-students. So when I accepted this invitation, the general chair, Hirata Sensei generously said that my talk about symbol emergence in robotics would give some inspiration to the participants of CMMR. So that I hope so, and I'll do my best. So, okay. So that in such sense, so this talk is not directly related to computer music, but I appreciate it if you find some relationship between my talk with your interest. And if you have any questions, please don't hesitate to ask after this talk. Okay. So before getting into the main part of my talk, let me introduce a bit old study of mine about automatic music composition. This is one of my few studies of computer music. Let me play a video which we created for a domestic conference 10 years ago. This is an example of automatic music composition. Thanks. So this is the melody was generated from probabilistic generative model. The probabilistic generative model is one of the keywords of this talk. And actually, all parts of this music was not generated automatically. Only melody was generated. So in this model, the VP non-parametric Bayesian language model, so called variable order Pitman language model, that was trained using around 30 scores. And code progression, actually code progression and the lyrics are given. And using these probabilistic constraints, so we use the unigram rescaling for making the code progression that affect to the melody generation and the lyrics as well. So actually, accompaniment is manually given after melody is generated. So in this way, and actually the melody generation is derived as a blocked give sampler. It's a Monte Carlo MC algorithm. Okay, so I want to emphasize that this is developed purely based on probabilistic generative model, which is analogous to language generation. So when we think about the language generation task, so a sequence of notes corresponds to the sequence of words, and a code is corresponding to the topic of a document. And the constant, actually the constraints given by lyrics are almost same as the constraint of the number of words in each sequence, each sentence. So that's almost also why our group conducted this research 10 years ago. So the main topic of our research group is kind of language acquisition and symbol emergence based on probabilistic generative model. So I have been really interested in the structural similarity between language and music. But today, our talk is not about directly the music, but the language acquisition and symbol emergence. So let me start the main part of this talk. First, I would like to talk about what is symbol emergence in robotics and its relationship with the probabilistic generative model. So anyway, first let me show some videos to give some flavors of our research. So how can we make a robot more cognitive and developmental based on its sensory motor experience? So it's a central question in cognitive and developmental robotics. So these are the video, the recorded through our research. But I will explain the detail of some of them at the later part of this talk. Anyway, we use these robots to study artificial intelligence. So, okay, let me move on to the background of our research. Actually, we researchers in developmental and developmental robotics and symbol emergence in robotics are very much interested in computational understanding of human mental development. And actually, a human child acquires many physical skills, the concepts, and knowledge, including language, through physical and social interaction with their environment, and just from their sensory motor information. So, so we would like to obtain an understanding of the computational process of this kind of mental development, and including language acquisition. So it is essential to develop computational robotic models that can reproduce such a process. So when we think about this point, so first let me start with this very abstract figure to remind an important aspect of cognitive system and cognitive development. So an agent, this is corresponding to a robot or a human child. So an agent is in an environment. So usually the agent has a sensory motor system and is connected to the real world environment using sensor and motor information. So this is a continuous interaction with the environment. So based on such kind of sensory motor information, many kinds of cognitive capabilities, including motor skills, perceptual categories, and planning capabilities are gradually acquired by the agent. So they are ranging from the low-level cognitive capabilities to high-level ones. And note that some sensor information comes from not from the physical environment, but from the other agents. So sometimes we call such a sensory motor interaction a social interaction. So based on such a social interaction, the agent learns to sometimes estimate the other interaction for collaboration, and also acquire language. And actually, the language symbol system is a kind of the general view of the general term, than the language. So here, of course, language acquisition, language include various components: syntax, lexicon, the phonetics, semantics, and the pragmatics, and so on. So the point is that the even high-level cognitive capabilities, including language, is organized in a bottom-up manner based on sensory motor information, because we cannot get anything other than sensory motor information. Okay, so on top of that, so that these cognitive modules are also mutually dependent. So, for example, perceptual category affects lexical acquisition, and lexicons affects the perceptual category formation. And it has also been claimed that the syntactic parsing and planning capability are mutually dependent, and so on. So it's also important to study them together. It's also important part. Okay. So based on this idea, so this kind of bottom-up view is not limited to cognitive dynamics of individuals, but also symbol systems, for example, language in our society, are also organized in a bottom-up manner. So the symbol emergence system is a kind of the integrated view of the cognitive and social dynamics of our symbol system. So to understand our cognitive systems that integrate symbolic and physical knowledge, I believe that we need to model the bottom-up formation of not only the internal representation in our cognitive system and the organization of symbol systems in our society. So if we can obtain such computational or constructive model, then we can reproduce the phenomena in a real-world environment. So therefore, we have been studying the symbol emergence in robotics. Okay, the symbol emergence system. I will not talk about much about the symbol emergence system. This kind of philosophical view itself. But today I will be talking about the symbol emergence in robotics. Anyway, from this view, I want to have a discussion about what is intelligence. Again, let's repeat this very, very fundamental and basic question. So in spite of the future progress in AI, the view of intelligence is often kept to be very simple. That's just a function or mapping. Most of AI technologies, including visual recognition and automatic speech recognition, are regarded as a kind of function mapping from, for example, the image to label data, or I'll say the speech signal to the transcribed sentences. So it's always a single purpose and task-oriented, and intelligence is almost regarded as a kind of procedure and no autonomy. But when we look at our children, so children developed using its own sensory motor experiments as an autonomous cognitive system without any manual level data. The cognitive system is not a single task-oriented, and the cognitive system itself is organized based on the sensory motor information flow, and it has autonomy. So there's a huge difference between the current view of intelligence and what we are, I think. So, okay. So, and I think, so to model the right-hand side, so probabilistic generative model is a very suitable approach, I think. So actually, this way of thinking is resonating with the view of generative view of cognition. And recently, generative view of cognition is gathering attention in brain and neuroscience as well. The free energy principle proposed by Carl Friston is recently very popular, and the predictive coding and the world model and are related to keywords. I think that some of you may know as these keywords. So actually, before getting into the detail, maybe some of you may not know what's probabilistic generative model. So actually, that it's a kind of Bayesian approach, and I think Gaussian mixture model is a well-known probabilistic generative model. Maybe some of you might have used Gaussian mixture model for clustering tasks. So actually, in Gaussian mixture model, this is a kind of the generative model. This is a kind of graphical representation of probabilistic generative model. So it is called a kind of probabilistic graphical model. But this is representing a kind of probabilistic generative model. So this shows the kind of generative process of the observations. So actually, sometimes people tend to think GMM, it's a kind of the clustering method. But interestingly, the optimization criteria of GMM is not the success rate of clustering, but the probabilistic generative model is GMM is trained to be able to predict or generate the data observations. So this is the general view. And actually, as a result, GMM can perform the clustering. Okay. So if we go back to the cognitive modeling, so let me explain a very rough sketch of modeling cognitive systems with probabilistic generative model. So roughly speaking, probabilistic generative model has two types of variables: observations. This is a kind of sensor motor information, observation, and the latent variable. So this cannot be observed, and that should be estimated. So we assume that the latent variable generates or predict the observations. So our cognitive system infer the latent variable using the observations. And please consider that the latent variable is the kind of the internal representation of our cognitive system. And they are trained to predict the observations. Okay, this is a very general view. Okay, so first let me show a video of our experiment. So this is a very old, I said about 10 years ago experiment. So the robot grasps the pet bottle and get the haptic information. And the robot shook the bottle to get the auditory information, sound. And the robot looked at the bottle from different directions and got visual information. So what the robot is doing is just interacting with the objects. But after the interaction, and the robot try to model the multimodal data using this generative model, multimodal Rajan-Dirichlet allocation. So this can integrate the multimodal sensor information, and this is a kind of extension of topic model, the LDA. I think some of you have used this kind of model, but this is a type of generative model. So as a result, so this is an example of categorization result. The robot could find these clusters without any label data, just from sensory motor information. So of course, recently the multimodal machine learning become more and more popular, and like multimodal variational autoencoder and many other methods can perform this kind of task. But the important point is that the robot, they do not need the future human teachers instruction to form this kind of internal representations categories. Okay, and also it is very important starting with real-world embodiment and the sensory motor information. It's very important for our research. Okay, so this maybe you got the kind of flavor of our approach. Okay, so so today I want to talk about the language learning, and also how to create the more complex cognitive mode system. Okay, so let me move on to the next topic. So actually, language acquisition is also regarded as this kind of cognitive modeling. This kind of can be studied using a similar approach. And let's take another example of bottom-up unsupervised learning of words and phonemes. Okay, in a conventional approach in AI, automatic speech recognition, ASR, and speech synthesis, basically the text to speech. So benefited from the transcribed data by preparing pair of speech signal and transcription. We can optimize the ASR, automatic speech recognition system, or text-to-speech system. So actually, we can prepare the transcription, and if we get the speech signals corresponding to the text, so we can optimize this function. And we can get, roughly speaking, we can get ASR system. And if we, in an opposite way, so we can optimize the speech synthesis system. So this approach is somehow very natural, and most of the people, researchers related to the ASR and text-to-speech are taking this kind of view. But when we look at our children, this is like somehow a natural approach. So children do never have transcribed data. So actually, before children become able to read transcription, sentence, written text, they can learn words and phrases and become able to use them just from speech signals. Children, in this sense, children are performing unsupervised learning for spoken word sentence production without transcribed data. So maybe that children can find some structure from sensor signal and the speech signals, and obtain the unit of words or unit of phoneme and something like that. So this is a kind of our motivation. So how can we create this kind of computational model without text, without transcription? So actually, considering the language development of infants, word discovery task or word segmentation task, that is a critical task. When parents speak to their children, they really use isolated words. I mean, for example, the pen or apple or something like that. So just a single word. So actually, the usual parents rarely speak this kind of isolated word, but a continuous word sequence they give. So therefore, word segmentation is the primary task of language acquisition by children. So they have to perform word segmentation without pre-existing knowledge of vocabulary and even phonetic systems. They don't know phoneme as well. Okay. So, and also, of course, they don't have access to label data. So how can we build this kind of system? So, okay, so what kind of assumption can we assume for speech signals to perform unsupervised word discovery? So I come up with this idea, and double articulation structure gives us a cue. So actually, interestingly, all human language have a double articulation structure. And the spoken sentence is considered as a structure, sequence of phonemes, and phonemes are grouped into words. And interestingly, people give them meanings. So this two-layer hierarchy is often called a double articulation structure. So in some sense, from the machine learning viewpoint, so the analyzing speech signal and find latent double articulation structure is corresponding to the phoneme and word discovery. So we developed a probabilistic generative model for time series data having a double articulation structure. So this is a paper we published about 5 years ago. And this model is called hierarchical GHL process hidden luggage model. But the generative model itself looks a bit complicated. But simply speaking, the model integrates knowledge about the language and the phonemes into a single model. And there is almost no other assumptions. This simply integrated, simply model such kind of the double attribution structure. And actually, we derived the inference procedure, the give sampling procedure for this generative model simply. And this is a kind of schematic view of our model. And actually, the in-speech recognition study, the knowledge of phoneme, roughly speaking, knowledge of phonemes are called acoustic model. And the knowledge of words are called the language model, including the transition probability between words. So what we want to do is let's learn the acoustic model and language model just from speech signals. Okay, so actually we could do that. And in this paper, we show that unsupervised learning, unsupervised learning could become a competitive with very conventional off-the-shelf the speech recognition system, even though it's unsupervised learning. But to be honest, in this evaluation, the speech signal was very simple, just a vowel sequence, because and the data set was very small. Okay, but I think that at that moment, this result was somehow surprising. And actually, after this kind of deep learning era, now this field become hotter and hotter. And self-supervised learning-based methods have also been proposed by many researchers recently. So, for example, Facebook AI group published a paper about Web2Beck-U this year, which have great performance in unsupervised learning of speech recognition systems. So this research field is changing rapidly, and I think that somehow the label data become less and less important these days. Anyway, this is a talk about the word discovery and phoneme discovery. But to be honest, such kind of learning process, when we study such kind of system, we found that it's very difficult to make the robot obtain the word and the phoneme in a sufficient manner and in a satisfactory manner. So actually, the speech signal is very noisy, and there is so much uncertainty and ambiguity. So actually, the researchers in developmental psychology, they're pointing out not only such kind of the probabilistic information on the speech signal, but also the children make use of prosody information, prosodic cues, and co-occurrence information, co-occurrence cues. So next, I want to focus on the co-occurrence cue. And what is a co-occurrence cue? So, for example, when a person talks to a robot or a child showing an apple, the probability that the sentence contains a word related to the apple is high. If a robot can make use of such information, so the kind of the object information, to find words from a speech signal. So if the robot can do that, maybe the word that can help the word discovery task. And that's a co-occurrence cue. However, so we are talking about the kind of the learning process, language acquisition process. So why children and robot know that this is an apple? How say? This is an apple before obtaining the before learning the word apple. It's very confusing problem. But however, as we explained in the introduction, for example, the object category can be formed without lexical information, word information, just from sensory motor information to a certain extent. So the one of the solution is multimodal object categorization. To use multimodal categorization with word and phoneme discovery. Okay, so actually we combined the multimodal categorization. This is a kind of the acquisition of object concept and word discovery task, word discovery system. So this is a graphical model, probabilistic generative model of the system. So it looks very complicated again, but roughly speaking, this part is corresponding to the automatic speech recognition system, and including word discovery. And this part that is corresponding to multimodal object categorization. And these two models are sharing one node. This is about words. Okay, so when the robots try to find words, they use both information, so the speech information and the multimodal information. And by inferring the words using both information, the robot can effectively acquire words. That's the kind of trick. And actually the robot could find the multimodal object category and words simultaneously. And interestingly, so that if we make the robot learn that word discovery and multimodal categorization simultaneously, actually each can help each other, and the performance is improved. So this is an interesting point of this kind of the complex, the multimodal unsupervised machine learning system. So this is about word discovery related to object categorization, but also not only object category, but also other words and categories important in our daily environment. Actually, the in-service robot demonstration or tasks, the one with the most popular task is to ask a robot, please go to kitchen and bring me a pet bottle or something like that. So in such a case, the sentence naturally involves object, pet bottle or some object, and place, so kitchen or lobby or something like that. So because of this, we have also been studying special concept formation and the lexical acquisition of place name. So for example, we developed a machine learning method called SPUCO-SLAM, special concept formation with SLAM. And and this can form a map, find a cluster of positions, and discover words representing places from speech signals simultaneously by integrating multimodal information. So actually, so let me think about. Let's think about before getting into the detail. Let's think about what's place. What's the concept of place? So how can a robot learn the names of places in an unsupervised manner. And I found that actually when in the very ordinary study of the service robotics and the intelligent robotics, robots tend to form this kind of map, 2D map or 3D map using SLAM. It's a very popular technique. And the robot become able to estimate where he is, where she is, as a kind of XY coordinate, okay? XY coordinate, the position. So the question is, so for example, so please, when we ask the robot, please go to kitchen. Now, what is the position of kitchen? Kitchen is some specific XY coordinate. So I think that's a kind of nonsense. So we humans do not interpret the kitchen as an XY coordinate position in Cartesian space. The concept of the kitchen is something richer, involving an area and names and the visual image, sound, smell, and so on. Actually, when we visit my friend's house, and we can immediately estimate which part is a kitchen. Because we can see the refrigerator and oven, microwave, and the fry pan and knives and so on. So by using such kind of visual information and the knowledge of object, we can estimate these places, these parts are kitchen. So in some sense, place, the concept, special concept is also multimodal. So based on this kind of idea, we developed the probabilistic generative model for learning the special concept and make a robot acquire the words representing places. So this is a graphical model of SLAM. Maybe it's too complicated, but roughly speaking, this part is representing the SLAM, map construction and self-localization. And this part, the red part, is corresponding to the kind of cluster of positions. So some region is corresponding to kitchen. So this is representing such kind of part. And this blue part is representing visual information. And this yellow part is representing a language. Okay, the observations are just a kind of the distance sensor and action information and the visual information and the speech signal. Just from these signals, the robot try to form, the robot can form maps and estimate its position. And time to time, the user of human participants talk to the robot and, hey, you are arriving the kitchen, or here, this is a copy room, and so on. So by hearing such kind of speech signals, the robot try to find words, and obtain lexicon. So to be honest, at first, the robot just knows the knowledge, just have the knowledge of phoneme and syllables. So the robot does not have any knowledge about words. But from this observation, the robot can estimate, infer the knowledge, the list of words, and obtain the correspondence between words and the kind of region and the visual information. Okay. So this is a study about the online special concept acquisition method. Okay, so actually, these are the study about the word discovery related to multimodal information. But when we created this kind of demonstrations, we found that we cannot understand what's happening inside of the robot. Robot. So in this approach, with this approach, robots can automatically learn something in their brain, but that cannot be observed in some sense. But think over this point, I thought that may be the future challenge of AI robot system. So AI robot system will be expected to learn many things through daily interaction. But if we don't know anything about what they learned, what they acquired, so it's not so transparent, and it sometimes, makes us confused. So, but interestingly, robot, differently from other software AI, robot share the same environment with us. So maybe we human users can jump in the informational space that related to the robots. What robot learned. Okay, so we introduce the AR display. So we try to visualize the robot's knowledge and the memory with HoloLens. So this is a very simple demonstration. We show the knowledge the robot obtained about the place concept, special concept, and the place name through HoloLens. And actually, the user can understand in what way the robot recognizes the world field, the shared, this task field. So this shows the robot think this part is a kitchen or this part is a sofa and so on. So maybe this is just a kind of demonstration on the system, and I think this is this kind of research is also important for enhancing the human-robot interaction. And oops, sorry, the sound is too loud. It's okay, but if it's too loud, please make the volume smaller. Sorry. I'm sorry for maybe the sound was too loud, but actually this is a kind of the video about the World Robot Summit, and actually we developed this language acquisition system, and actually this was a kind of scientific research, but at the same time I think this kind of adaptive cognitive system can be used in the future human-robot interaction system. So as a testbed, we introduced this kind of system partially into the convenience store environment and attended the World Robot Summit. So which is a kind of the Japanese government sponsored by the Japanese government, the robotic competition held this year and 3 years ago, and we won the gold prize there. Anyway, okay, so I have 20 minutes more or 10 minutes, maybe. Okay, so let's let me move on to the next topic and something like complementary topic. Actually, as I explained, we have developed several kind of the complex or integrative cognitive model that based on probabilistic generative models. And this is what I showed before. But maybe developing this kind of system is very costly. Actually, our system become more and more complex, and actually this model is developed by the PhD student of mine, and he is now assistant professor in my laboratory. But I think nobody other than him can build this system. And because it involves the SLAM and the visual recognition system, and speech recognition system, and the word discovery system, and the clustering, and so on. And Bayesian inference algorithm for this total system should be derived. So it's a super tough job. So to promote this kind of research, we need to have a more cost-efficient approach to develop this kind of system. So when we look back and look at the previous models we developed, and actually this one was explained in the object concept-based word discovery task. And this is a SLAM. And this is another graphical model that proposed in the different paper. So developing an integrated cognitive system from scratch requires huge cost, i.e. labor force. So, but when we look at these models, we found that actually most of them are just a composition of elemental models, So for example, this model connect multimodal LDA for object categorization, and this part speech recognition system with language word discovery. And SLAM, and the SLAM is a combination of SLAM, Gaussian mixture model, MLDA, and ASR. And this model is created by combining 3 MLDAs. Okay, so connecting cognitive modules developed as probabilistic generative models and letting them work together as a single unsupervised learning system. If we have this kind of system framework, we can easily develop more complex system. Okay, so we propose the framework circuit. This is an architecture for connecting stochastic models to realize a large-scale cognitive models. And actually, recently, 1 year ago, in 2020, so we extended this idea to deep generative models like variational autoencoder. And now variational autoencoder can be a part of this kind of system. So I think this kind of approach can extend possibility to create more, integrative system. Let me skip some slides because of time constraints. And actually, why we are so interested in the probabilistic generative model and probabilistic model-based approach. Actually, in some sense, so supervised learning and reinforcement learning and unsupervised learning. This is a very popular 3 division of machine learning. But actually, these are regarded as part of probabilistic modeling and in fact probabilistic generative model. Maybe you can notice that the supervised learning it's just a kind of has a modeling the posterior distribution, conditional distribution, and the unsupervised learning is to model the joint distribution. And what reinforcement learning? So you may wonder how reinforcement learning can become a part of unsupervised learning or a probabilistic generative model. So actually, I think I will quickly run through this point. This paper is very informative, and Sergey Levine wrote this tutorial paper. Actually, from a mathematical viewpoint, reinforcement learning can be reformulated as a probabilistic generative model-based modeling and Bayesian inference. So this is often called the inference control as probabilistic inference. So based on this kind of idea, for example, in SPCO/SLAM, so planning can become a part of this kind of unsupervised learning. That, for example, when the robot learn the many place names and special concept like a toilet or kitchen and so on the map. So, and after obtaining the knowledge of kitchen, we can ask a robot to go to kitchen. But conventionally, this kind of the planning process should be performed performed using A-star algorithms and some other independent planning model. But in this model, by following the idea of control as probabilistic inference, the action sequences can be inferred as a Bayesian inference in the same way as other inference procedure, the conditioned by the kitchen information. So I mean if the robot can find the trajectory to the kitchen using Bayesian inference. So we propose a SPCO-Navi. This is something like that. Anyway, so and I think currently, so even though it was the generative model itself is large, but what the system can do is just learn place name and object name to go to somewhere. So it's less capable than human. So far less capable than human. So maybe we should try more and more. And lastly, I want to talk about something, the future perspective. So, and actually, we wrote this kind of, we wrote a kind of interdisciplinary discussion about simple emergence in cognitive developmental systems on this paper. And if you are interested, please have a look. And also, so today I talked about something about language, but basically the NLP, natural language processing, and actually linguistics, and robotics. So there is a huge community gap between them. But actually, when linguists tend to study the sentence in the text itself, but rarely treat multimodal data itself. So robotics people tend to deal with the multimodal data, real world data, but not so get into the detail of the language. But the language can work in the real world environment. We use language for tackling with the real world environment and collaboration in the real world environment. So I think the bridging language and the robotics, so it's a crucially important in future study, I think. And this is the survey paper published in Advanced Robotics. And happily, this paper awarded Best Paper Award this year as well. Okay, so also when we try to build an integrated cognitive system, so what kind of function should be implemented and how we should connect each module? That will be a question. So also the learning brain science is important or effective approach. So this is still under review, but the preprint is published in, it's called the whole brain probabilistic genetic model. Okay. Anyway, I think the time is almost over. And before finishing my talk, I want to revisit the notion of simple emergence system. So this is I sometimes show this figure, and maybe many people don't know what is this. So actually, simple emergence is fundamental understandings of the system that enables us to communicate each other using symbols, signs. So a human forms the categories or concept in a bottom-up manner through an embodied physical interaction with his or her environment. And such elements, categories or concepts formed in his or her cognitive system become a basis of human symbol system, I think, in the language. But it's a kind of phenomena happening inside of individual. So next, even though concepts and categories based on an individual cognitive system are totally self-enclosed existence, using formed concept and categories, people can describe their situation and desires using many types of sign. But they can interpret the sign using formed concept and categories. The process gives them very primitive capability of semiotic communication. So in this way, symbol system used in the community is gradually organized, I think. The organized symbol system should be shared among communities. And, and sharing symbol system means that each agent should use and interpret the signs in the same way, in some sense, in the same way as others. To join this community, each participant have to give up a certain amount of their degree of freedom in expression and the use of interpretation of sign by following the shared symbol system, a custom or culture. So, and as a result, the system has a kind of bottom-up dynamics of organization of a symbol system and top-down constraint, top-down dynamics of constraints. This kind of loop is often called a micro-macro loop in complex system, a science of complex system. So, having a micro-macro loop is a kind of condition of that a system, a complex system becomes an emergent system, the complex system having emergent property. So we call this system as an emergent symbol emergent system. So maybe this is a kind of a philosophical and a systematic view of our society and the basis of our language use. So, and I think, so this is just a comment almost. I think this kind of culture dynamics is also important for music. So the interpretation of music depends on culture. So I don't know to what extent the analogy between language and music is appropriate, but I'm happy to discuss with you about these points as well. So of course, we also have a kind of this kind of social dynamics using probabilistic generative model. But how to say, so this, if I try to talk about this, I need 20 minutes more, something like that. So I want to skip this point today. Okay, this is almost a summary. And okay, I want to conclude this talk. This is a summary and some challenges. So that's all. So maybe time is a bit over, but thank you very much. That's all.
Thank you so much, Professor Tadahiro Taniguchi. So I would like to put hands.
Yep.
I was very impressed by the World Robot Summit video because it seems to be that the something like the movie's tornado, the very dramatic sound and images. That was very impressed to me. Anyway, so someone may raise your hand if you want to ask some questions.
Any question is okay.
Yes.
Even if it's not so much related to this talk or concrete topics.
Any questions? Okay. So I have a question. Also, you mentioned at the very last section the analogy between the robotics and music. And you put emphasis on interactive cognitive model to acquire the new concept in languages. And please imagine that's the special situation. The children just hear the music and without any interaction or without the sensory motor information, just the children or baby listen to music only. And can he or she acquire the concept related to music, like melody, harmony, or rhythm? According to your theory or framework, the human must have some sensory motor information to acquire the new concept, which may call something like embodiment. And but please imagine that such a special situation where the baby just listening to music, can he, she learn music like us?
Thank you very much for pointing out a very important and great point. And actually, that's also I have been wondering. So, what's to what extent that analogy can be held? And actually, when we think about the language and the words, so we can recognize, we can think about it from the viewpoint of a symbol. And in the Persian semiotics, the symbol has 3 elements, and sign and object and interpretant.
Interpretation.
So, interpretation, yeah. It's also called interpretant. And so like something like an apple is the word apple can represent apple, such kind of stuff. So actually the kind of perception of the external world is a kind of starting point of our research. But how to say, the language word is often regarded as such kind of reference. But music, so music is, how to say, has its meaning with itself, or how to say, usually that does not represent something outside. So that's always make me confused. But something missing here is a kind of the observation of internal state. So like an emotion or a kind of the how to say, internal reaction. Like it's so, how to say, itchy, or some, so say it's somehow make me excited. Or I think that if we involve such kind of internal sensation, so maybe we can find the relationship between the music and the language. And I think from that viewpoint, maybe children can form some concept about music, even without interaction with other people.
Also, okay, thank you so much. And also you put emphasis on the social dynamics.
Yeah, that's right.
When the robot can may define some the common knowledge or something like that. And also I think that the human or baby need to communicate with other people or the father and or mothers to acquire new concept, in particular music.
Yeah, I think so. And actually, that how to say, in symbol system, so the kind of, I think basically, so even in this kind of language acquisition process, so actually category can be formed individually, but a label. So how we call that cannot be learned so individually. So actually such kind of how we call that, this is a kind of social rule And actually, that rule is changing over time. So that inevitably requires social dynamics.
Yeah, that's true. I think so. Thank you so much. Okay, so Nakamura-san, do you raise your hand? So please go ahead.
Thanks.
Do I have some time for question?
Yes, you
Okay,
do.
yeah. Thank you, Taniguchi-san, for a very interesting talk. So I'm interested in the social communication or social relations or language acquisition. I think so. You emphasized the unsupervised learning is important.
Okay.
But I think supervision is also very important for actually language acquisition for human. For example, when we have like children grow up in wild or isolated from the human society, or they cannot speak language, right?
Right.
So, and also we have many languages, and categorization is different among, I mean, we have common categorization, but we sometimes have quite different categorization scheme across different languages or different cultures. So how can you explain these aspects?
Thank you.
What do you think? How much supervision is important?
Thank you very much for very important question. And actually, my answer is clear. And we need to distinguish two notions about supervision and supervised learning. So in machine learning, AI studies, supervised learning is a kind of mathematical term. So there is an input data, and the output data is, ground truth output data is given as the label data. And such kind of mapping should be trained through the function optimization. This is a notion of supervised learning. So it's nothing to do with the phenomena of the supervision. So if there is a mother parent, and the she or he is interacting with the children by showing something and saying something. So that can be modeled both by unsupervised learning and supervised learning. Okay. So from that view, so supervision by parent or by other people is important. And I think such kind of thing that should be modeled as unsupervised learning in some sense. So actually, please look at actually left-hand side. This one is very much similar to the supervised learning scheme. And the right-hand side is very much similar to the unsupervised learning scheme. So actually, in right-hand side setting, the people can have an interaction with the children. So, but for example, I show this, this one. So, parent can interact. Let's consider this left one is parent and right one child. So actually, the parent can interact with children by showing object and by saying something, and that can arrange the sensor motor information for the child, and that can accelerate children's learning. And but what I want to say is that we cannot inject the kind of direct information to our brain inside of brain. So what supervised learning in machine learning or pattern recognition to do is something like that. So injecting some artificial the label data to the kind of inside of brain to make the children learn something. Such kind of supervision is not so natural, I think. That's my starting point. But I don't know if my explanation was clear or not.
So my question was, so can you like model the different categorization scheme or individuality of real humans' ability to like communicate and think using language? I think, yeah, that's a question. So
individuality.
Yeah, so I think so. Like people in different cultures, they share a lot of concepts, but in some cases they have quite different categorization scheme, and that's I think because they are supervised by their parents or their community. That's a kind of culture.
Yeah, of course.
So do you also have models to explain those different?
Yes. That's actually what our symbol emergence system model try to reproduce. So actually, to my understanding, to explain such kind of phenomena, so unsupervised learning based or this kind of probabilistic generative model based approach is more appropriate to consider to model such kind of system. Actually. So it's actually the supervision. What you mentioned with the word supervision. So
yeah,
isn't
that point? I just wanted to, for example, if you can quantify the amount of supervision you need to explain this kind of cultural differences, that would be very good. I mean, using your model. So yeah.
The quantification may be the also future challenge, maybe. But yeah, so it's very much I'm interested in.
Thank you very much.
Thank you so much. Any other? Okay, please go ahead, Kitahara-san.
Thank you for your very interesting talk. I listened to your talk while thinking about the relationship or connection to music. So, and then, you know, it might be something like my personal impression or thought rather than question, but so I'm interested in what kind of representations non-musicians have internally, because even though they have not learned do re mi fa sol la si do, they can sing a song, sing a melody. So you know, so even though they don't have a concept or a label, a discrete label of pitch or rhythm or something like that, they have something internally. So they acquired something about music. So I don't know I have no idea about what it is, but this concept of the research of concept of symbol emergence is very helpful for tackling this problem. Yeah, so just my comment.
Thank you very much for your very interesting comment. And yeah, that's a great question. And actually, regarding the kind of discretization or kind of discrete level. So I'm recently, so I'm so I'm against the idea of that in our brain that there are some discretized symbolic system. So I think everything should be continuous. But the language and the observation itself is somehow discretized. So like there is a words and phrases. So the class of phonemes, there is some sort of category. But I think, I don't know, my answer will not be perfect, but such kind of something internal system or internal knowledge about the language should be organized automatically. And such kind of dynamics would be similar to the learning process of music. Of course, the do, re, mi, fa, sol, la, si, do, maybe that will help the people to recognize what they learn systematically. So of course that it's very similar to learning written language. So before learning written language, maybe children do not conscious about such kind of systematic knowledge. So I think it's a very interesting crossover between music learning and language learning. That's my comment.
Yeah. Thank you very much. Yeah, I agree with it. Yeah, thank you very much.
Okay, thank you so much for your presentation, Professor Taniguchi. And also I'd like to thank you all for audience for giving many the valuable questions. So I would like to thank Professor Taniguchi by putting the hand again.
Thank you very much.
And as like the other sessions, we will have the breakout room post session discussion. So you will find the breakout room named invited talk 2. So if we want to talk more with Professor Taniguchi, please go to the breakout room named invited talk 2. Okay, so thank you so much. Okay, Professor Taniguchi, please go to the breakout room.
Okay,
Can you?
Thanks.
Thank you so much.
Thanks so much.